Good day, everybody. Today I want to look at 5 integrals from the Berkeley 2021 final round of their Integration B. Came across this video. This one wasn't too bad. They were close. Does need one fact that isn't too common. So the key idea on this one is that the integral of a sum will be the sum of the integrals. That's always true for finite and for infinite. This is actually absolutely continuous, so there are some theorems about when you can change the order of integration and summation, but here we can. So I'll change it to a sum of integrals, and this is a constant with respect to x, so I can factor that out. So we just need to integrate all these signs. We'll just do a nice substitution. U equals 2n plus 1 over 2, and then x, whoops, and then du is 2n plus 1 over 2 dx. So 2 over 2n plus 1 du is dx. And then my integral, I'll just look at this integral. It's going to be the integral from 0 to 2n plus 1 pi of sine u du. Oops. And then I've got this constant out front, 2 over 2n plus 1. And we can either do the integral. I'll leave that to you. I'll just do it by reasoning out that I know like when n is 0, I'm integrating from 0 to pi, and the integral of sine from 0 to pi is 2. But if n is 1, I'm going from 0 to 3 pi, which is 0 to 2 pi, and that'll be 0, and then pi more. So it's pi more than 2 pi. So it's like integrating from 0 to pi. And so that'll be 2. And if I integrate, if n is 2, that's 5 pi. So that's 0 to 2 pi twice, and then 0 to pi one more time. Right? 0 to 5 pi, twice around the unit circle and once more. Or I guess thinking of the sine wave, 0 to 2 pi, that's 0. 2 pi to 4 pi is 0. And then 4 pi to 5 pi will be the same as 0 to pi. Anyway, so this will be 2 for all n. And we got this out front. You could do antiderivative, but let's argue this way. So now I'm going to multiply by 4 over 2n plus 1 times this, and I'm going to flip this up, and there's a 4 over 2n plus 1 being squared right here. So if I flip that up, I got 2 times 4 times 4, and I got 2n plus 1 cubed on the bottom. So if I put this in for the sign, 4 over 2n plus 1, I'll get 2n plus 1 cubed, I'll get a 4, a 2, another 4, and a negative 1 to the n. And so if I write out what this is, since that's cubed, this is 32. And then when n is 0, I get 1 over 1. And then minus 1 over 3 cubed, plus 1 over 5 cubed, minus 1 over 7 cubed, and so on, all the odds. And that actually equals pi cubed over 32. So that's not too well known, so I don't know if that was supposed to be known or what. I'll look it up real quick here. So there's our rule that we need, some others. I also want to look at that integral in a different way The integrand is a sum of sine functions, which you might know is kind of a Fourier series way of representing functions. So here's the sum from n equals 0 to 4. Keep it small for now. And if I look at the plot of the function, it looks like this, almost triangular. Let's put in a few more terms, well, many more terms. Let's go to 40. And notice the base is going to be 2 pi. The height will be pi squared. So the area of that triangle, 1/2 base times height, is going to be pi cubed. And that would be the integral of the function, the area of that triangle. Let's do a few more here. If I go to 400, there's the plot. And so if I evaluate the function at pi, we've been getting closer and closer to pi squared for the peak. So maybe one more here. 4,000. Take 4,000 terms. And we're getting even closer to pi squared. So the more terms I take, the closer we'll get to pi squared at the peak. If you just go to infinity, then you get essentially a perfect triangle. If I plot over a bigger range, say -12 to 12, why not? Then that's the Fourier series. Again, base 2 pi, height pi squared. Integral is the area under the triangle. 1/2 base times height is pi cubed. So that was our penultimate integral. Sorry. So hope you enjoyed that. Keep doing math. Thanks, and have a good rest of your day.